I hope all of you can see my screen. Good. And if you have questions, you stop me. I will try to go as slowly as possible. And in addition of presenting, can you see my code very well, or I need to zoom? Let me zoom. Zoom in. Okay. So I think everybody should be able to see. So the first thing that you should do, and all of us do, I only have a few lines here. I don't have all the code. The rest I will write it with you. So the first thing you should do, and that's what is the good practice, is to set up what is known as working directory. And if you are on Windows like me, then you will have Windows user by default \, or you can use a /. So if you copy it, you will have to use a, I don't know why this is behaving that. You can use a / or \\. If you use only one \\, it will not work. So that's something you needed to understand. And you finish with the folder where your data is. So everything I will be reading it from this folder. And one shortcut on RStudio, I don't know if you know all this or not, is to run the code, you can just Control, Enter, and you have it run. Or you can click on this and you run it. But I prefer Control, Enter. So now I have my working directory set. And the first file I want you to read is the file known as a fish tree food. So you have, if I do this, I read that file. And normally there are other parameters like headers is equal to true and things like that, but they are by default. The other thing we want to know is how the data looks like. So you can do head fish and Control Enter, and we see that it has 4 rows. So we have each river and the abundance and the tree area. So I need to explain what this data set is. So what happened is they went to different rivers, measured the tree area and then the abundance of fish. And the idea is maybe when we have more shade, we have more fish. So we want to check if we can use tree areas to predict the abundance of fish. Basically, that's it. And like I said before even starting to do any linear plotting, you needed to do the scatter plot. And if I run, you get the scatter plot here. I took the time to label it very well. You have a fish, abundance, and tree basal, and the tree basal area, and so on. You could format this one to really reflect how it should be formatted, like the square, the 2 in square. I didn't. And then you have fish abundance. So this line is to write the linear model. To write a linear regression model, it is quite simple. I'm not sure, did John cover all this or not?
He did, but I'm sure people are still learning now, right?
So if John already covered it, then I can go a bit faster to just show maybe things that I don't know. So to write the linear model, you need the response variable and then the predictor, and then you just specify your data set. And the LM means by linear model. And so when you do it, you create this object known as linear model object. I run it first, and it doesn't do anything because it saves everything in this object. Yeah. We have that the intercept is 17 and the standard error, and it is highly significant in the abundance. So this goes to the table that you have before. Now, what happens is the intercept is something that is very interesting, right? So what we are saying is, even if we have, okay, let me reverse this thing, and I don't know, my computer is behaving weirdly. So what we are saying right now is, even if we have, let me reverse it, okay? I don't know if you understand what I had. So this one was predicting the tree basal area using fish abundance. But what I really want is the fish abundance predicted by tree area. So now we have different, and here you can have the model. I mean, I needed to change the labeling. Perfect. And okay, so let's me fit the model now. And what we are trying to see is, even if we have a zero, like a tree area, so we have a point here, it is still like a 0.7. So 0.7, it is up to you to decide if that's significant or not. If we decide that we are interested in 0.1, then we can consider it as significant. So what it means basically is, even if we have a tree abundance, tree area of 0, then we will have fish abundance of minus 0.9. Maybe that doesn't make any sense. Maybe it shouldn't be negative. So in any case, we can run this same model and try to remove the intercept, this intercept. I don't want it. And if you want to remove intercept, what you just do, you say -1. That's all. And if you say -1, this model is exactly the same, right? You have LM and I have it here. I just put the object directly in the summary. I don't know how you used, how accustomed you are to R. So now you have a different model. I will scroll up so you can see the two models.
I think you forgot to invert again the variables there.
Oh, sure. Thank you. So let me scroll up and up. I wanted to see those models side by side. So I run this one again. And what's happening to my computer? I don't know if you can see my screen. This is supposed to be a computer. So these are the two models. And what you can see here is we have with intercept. And the coefficient is this. And when I remove the intercept, we get this new model where the coefficient or the slope is 0.05, and this one was 0.08. Basically, so it is up to you to know how to do it and why you want to do it. My intention here is to show you how you can remove the intercept if you don't want it. Because it is not always that you want the intercept in your code. You don't want intercept. One way of removing it is like this. So you will force R to set the intercept to 0. Come on. And I was talking about the R square. We have an R square of 0.72. And then I just said the R square of 0.69. So here is the question. This is supposed to be linear regression, right? Because we only have one predictor. So why do we still have adjusted R squared that is lower? And the answer here comes from the fact that the intercept itself is considered as a predictor. So our prediction here has our regression has two predictors, the intercept and the variable itself. That's why you have adjusted R squared. I just want to make it sure that you understand it. And we talked about the residuals. So we needed to see if our residuals make sense. But before that, let me go back and I think I did it here. So I plot, we have the plot and try to put, needed to change it here again. I understand. I got a computer that is supposed to be a good computer, and it is worse than if I bought it on the market. So if we run, so this is our fitted line, and our data in the fitted line that goes along with. So the question is, how good is this line? So like I said, to check it, we need to check the residuals. So remember our model. Remember our model is here, and what we want is to check residuals. So I will go into some more details to explain why this object, what it contains. Fisher LM. So if you want to know what an object contains, you just click here and you have a lot of things. Don't be scared, okay? You have the first thing you have is called the coefficients. And then you have another thing called the residuals. And then you have another thing called the effects, rank, fitted values, and so on. So basically what it means is you can call all of these things on this object called the Fisher LM. And that object is just the result of a linear model. So if I want to see residuals, I just can select this and run just that one. So those are the residuals, and I want to plot them. So to plot it, I use this par. What it does is it will create one row and 3 columns. So let me run it first. So I run it. It will be showing here. So let me zoom on it. So I run it, and then I take from, I want the histogram of residuals to see how they look. So histo function will just give me the histogram. I run the histogram, and so we have the histogram of our residuals. You can change the name if you want to by, for example, main equal hist. Let me just keep it short like that. So I needed to define this again. And then now you have the name of your histogram. So you can change the X label and the Y label the same way. And now I wanted to plot the other things, if you remember, of residuals. So which 1, 2 of the object will just give me, this object has 1 and 2. Let me plot it first. So you get residuals versus fitted and the normal. So all these objects are in this thing. Fitted. You can get your model back. Basically, everything you need, it is already here. So if you are not sure what you have, you can come and explore the object and see exactly what is in it, what is not. You have fitted and fitted. So 1 and 2. That's the 1, and this is the 2. So you have residuals versus fitted. That's it. And then you get the QQ plot. That is the, it shows if it is normal or not. So now we can debate or argue if you think it is normal or not. So the first thing you can see is our histogram. Okay, let me pause. I did something that is not good. First of all, we have to acknowledge how many observations we have. We have 15 observations. So it means it is only 15. So it is very difficult to know if data is normal or not if it is only 15. Usually it is over 30 and things like that, that it really makes sense. So the histogram, we have
someone is saying something here, and I thought it's maybe good
I'm
to
having
already stop
challenge
them.
with the code in line 10. Line 10.
Okay, with the plot.
Yeah, so let me summarize that code. Basically, to make it the code easier, I don't know where you are getting a problem. Let me remove all this. That's the only thing you need to write on line 10, and that should work. You are just plotting this. I mean, because I have bar, so you are just plotting this. Everything else I put there was to give names and embellish it and things like that. You don't need all that. I hope it works for you.
Yes, it does. Thank you very much.
Yeah. Okay, everyone is following. I will pause because I assume that it is going naturally, but I pause and make sure that everyone is following. Okay, so no question is coming, so I suppose everything is fine.
Yeah.
So where were I? I was explaining you how to plot these things because I spent a lot of time explaining you about the residuals. So I found it was necessary to show you how you can represent it for your research or whatever you are doing. And so now you have the histogram. That looks fine. It looks like it is fine. And we have a histogram of our data, and it looks like it is quite normal. We cannot say anything about it. And for the data, we have a few issues, the data 26, 8, and 10. So what it is telling us is those data points are quite different from others. 6 are quite low, and the 10 is quite too high. That's the only information we are getting. And so we see a clear trend like points are something, but points in the middle tend to be quite far from the line. All of them should be around this line. That's it. And for our QQ plots, okay, I think it is fine. This model is good. I mean, it's not perfect, but it is good. And remember, we only have 15 observations. So it is normal that you have this kind of behavior. So that concludes it. So you can report your linear model. And what we can say in this case is the abundance of fish can be predicted as abundance is equal to minus 0.91 plus 0.08 the tree area times the tree area. Or if you want the intercept, then you will have this model. The abundant fish is equal to 0.05 tree area here. And if you have done this part like that I did, that is to divide or to partition this thing, then you need to turn it off. And there are many ways to turn it off. One of them is to just write 1, 1. It means 1 row, 1 column. If you don't do it, you will be struggling all the time. And so now we can see the model that we fitted, and we see it is a quite good model. So that concludes the section on simple linear regression. Any question?
I'm still having a challenge with the line 10. That's my only question.
Line 10. So
Yes.
what do you have written? Can you put in the comments what you wrote, your code?
Okay, I'll put it.
Okay, wait. Before going to line 10, can you run line 5? Okay. So.
Yes, I can write line 5. I already have the head. I've partitioned work at line 5.
Okay, so I just want to make sure that, and your line 5 looks like this.
Yes, I have it like that. 0.34 for abundance to 1.20. And I have 17.2 to 34.4. But it's telling me here that error in evaluating predicted variable, comma data, comma environment, then object abundance not found. And I have it properly assigned here.
Okay, send your code in comments and we'll see. Or
I have problem running line 10.
You have a problem on line 10 as well.
No, 21.
21. Histogram. What is your error message? So to keep it simple, I remove all the other stuff and keep it very simple. And remember, you need this object, feature LM, from the linear model. So you need to store the linear model response in that object. If you tell me your error message.
Okay, I've gotten the line 5 and I've plotted the regression. So let me find the summary now.
Oh, there's something for annotate. I didn't know.
Yes, I think I'm good now.
Okay. That was.
I need to quickly catch up.
Okay. Who else still has a problem? Banco. I haven't heard from you. We were waiting for your code and it never came.
Oh, sorry. Yes, I am the one talking now that I've gotten it. Then I've done the summary. So I'm on line 17 now.
Okay, so that's good. And there's someone else who had a problem with line 21. Is that okay now?
Yes, I'm okay now. I'm okay.
Yes.
Okay, so we can move forward. Anyway, you will have these files to follow if you need to. So I will skip the rest on linear regression because everything else is like how to calculate the slope and how to calculate. Those are meant to help you practice your R skills, like how to do those things actually. But it is not meant to, in real life, you don't do it. It is just meant to help you because once you start working and analyzing a lot of data, you need to write functions and you will have to learn how to do those things. I mean, you can get the slope directly from this object. Like I told you, everything you need is in that object. So let's say that you wanted coefficients. So if you remember what I told you those coefficients were. So I copy the object again, and then I call it. You put a $sign, and then you see everything you can call on those things. So I want coefficients, and you get those two coefficients. The intercept is minus 0.91, and then the tree area is 0.08. Let's say that I wanted the tree area. That's the second object. So I can just put 2. and then you get the true area. So let's say you were writing a very complex model, and then you wanted to get the regression and just use the slope of that regression and do something with it. So I can just do this in my model without caring what is the actual value. So it is very important that you save your linear model object and you know how to access each element of that model. I hope this is helpful. And the idea is you will need it at some point in your life, to analyze data. You will not be copying here and pasting, no. Good. So we move to multiple regression. Unless there is a question. Okay, I keep all this just for reference. And other kind of tricks, if you wanted to clear this console, Control L, it goes away. So for the multiple regression, the idea here, the philosophy, we will use the second data set that is salaries. So the philosophy behind it is that you completed your PhD and you just finish your last postdoc and then you get a new job. And your friend told you that they made $50,000 a year out of college and they make $100,000 now. And you are curious whether you will match or exceed your friend's salary. So your idea is you want to predict the salary of people based on the kind of discipline they are teaching in. Maybe teachers of forestry make more money than the teachers of computer science. So you want to use all that information, and the year since the person got the PhD, and how many years they were working, and then the salary based on the gender. And like many of you know, men tend to be more paid than women. So all that information, you collected it, and you want to predict the salary based on all that information. So that's the motivation behind that multiple linear regression. You want to predict the salary using all other information. So the question is how to do it. So the first thing to do is, now I want to write it with you. You will read the CSV, and you use tab to autocomplete, and then you just give it the name, right? In this case, it is a salaries. Why can I do this? Because I specified where is my working directory. And what I do most of the time is, I will call it salaries. And to put a data error, I don't know how you guys do it, but the shortcut is Alt minus. You get it at once. So the command is Alt minus. So I run it and I get my salaries. So here they are. And it is 397 observation and 7 variables. And like always, you need to make sure that your data looks like you want it. And looks good. You have the rank, associated professor. And so this is what I was saying about. These are categorical variables and the discipline. So they are categorical variables and you need to use them. So they are not linear, they are not numerical like this. Fortunately, R does it for you. But once you start going above and beyond in advanced science, you will have to start doing these things by yourself. So, and like before, we need to write a linear model, and it is the same thing. You just need to write LM, And we want to predict what salary can be predicted by rank plus discipline. Please spell it exactly the way it is spelled. So I look underneath here and I write, or if you are lazy, you can just copy. And, just copy, paste, and then come and put it last. And now we need to specify what is the data. Salaries. So this will give us our linear model. So let's call it all or salaries LM. And alt minus, and you get it. So we run it, no error, it means it is good news. So now we have our linear model. The most important aspect is we wanted the summary of our linear model. And if I run it, we get this model. So the interpretation of this model goes like this. It reminds us what is the model and a smaller idea about the residuals. And then it tells us what goes with what. If you see rank was the column name, this rank. And in rank we had, so let's see what kind of ranks we had before, okay? And then we go from there. And I think it is unique. Salaries. And I want the column rank. So if I run it, I will get the list of unique rank. So we had 3 ranks: professor, assistant professor, and associate professor. And now we come here and we check rank. We only have assistant professor and the professor. We don't have associate professor. So you may be wondering, where did it go and how will you know the salary of an associate professor? I wouldn't answer the question yet. And we do the same. Let's go to discipline. The other one that was not numerical was discipline. So I do the same and check discipline. And we get AB. So we have AB. It is only 2 disciplines we have. But in the result, we only have 1, B. So we don't have A. So, and for the gender as well, we have the same thing. Sex, we have male, we don't have female. The question here is, so what will you do? Let's say that you have an associate professor who is teaching discipline A and is a female. How will you predict their salary? Because you don't have it here. You have everything but that one. So the idea here is that is the intercept. The intercept is the base case. So let's say that if you have someone who has 0 years since a PhD and 0 since years since service, so this 2 will be just 0. And then they are a female, so male will be 0 as well. And they teach discipline A, so this one will be 0 as well. And the rank, like I said, they are associate professor, so this will be 0, and the assistant professor will be 0. So the only thing left will be this. So I hope you understand what is happening here. So to predict the salary of someone who is in that category, that specific category, that is, I will write it down so it is clear. How will you get the salary of a female associate professor teaching discipline A? That's the question. Because you don't have anything in this thing that helps you do it. The question here is what this model is really telling us. I wish I could write it. Let me see if I can write it using the annotation of this thing. So what this model is telling us is salary is given by intercept. So let's call it B0, right? Plus B1 rank. B1 rank associate professor plus B2 rank professor plus B3 discipline A. The discipline B plus yes another B4. You understand those B's are the coefficients, right? B4 years since experience. Years since the PhD plus B5 times years service plus B6 times sex mail. So that's our linear model. So that's what it is telling us, that when you take someone, you want to predict their salary, you will have zero, B0, that is the intercept. All of them will have it. And then if they are associate professor, then they will have B1. If they are associate professor, they will have B1. If they are as a full professor, they will have B2. So then this one will be 0. So they will have one of the two, not both of them. And if they are associate professor, then they will have none of the two. Then if they teach discipline B, they will have B3. If they teach discipline A, then this will be 0. And then since experience, that is just numerical. So all of them will have it. But if years since experience is 0, then this one will not exist. And then you will have B5 years since service. If it is 0, then it will not exist. And if they are male, then they will have B6. If they are female, they won't have it. So to get this one this question that I asked, how would you predict the salary of a female associate professor teaching discipline A? Then it will just be B0. So if we just change this question, it looked good when it had that background. Okay. Okay. Let's see if I can feel something in it. No? Okay. Anyway. So let's put it somewhere. So if we change this question a little bit, just a little bit, and say that the person, it is a female teaching discipline B, then their salary will become B0 plus B3. Then the salary will be, again, let me type, then the salary becomes, salary is equal to B0 plus the teacher discipline B, right? Discipline B. Yeah, plus 14,417. So let me put actual numbers and it will make all of us happier. 78,862.8 plus 14,417.6. That will be the salary if it was this case. So you have to understand that these things called rank associate professor, they are binary. So they are either 0 or 1. They are not anything else. So because now discipline B will become by a 1 here, this one will become 1. In my formula here, it will be discipline B. So this is term. Oh, I wish I could select it. I cannot select anymore. So this term, will become 1. So this one will be B3 will become whatever what I wrote, 14,417. I hope that makes sense and it helps you understand how to interpret multiple regression. And that's the key element. So let's say that you wanted to know what is the value of teaching discipline B. And that value of teaching discipline B is 14,417. So I don't care about anything else. What I know is teaching discipline B will make you make more than, will increase your salary by 14,417. This is very crucial information to have. So if I am going to choose to study, then I need to know that if I choose to study discipline A, I will make 14,417 less than if I choose to study discipline B. And the same thing it is saying here is men make $4,783 more than women. That's the information here. That everything else being equal, that they have the same, they are both, they have the same rank. They are maybe all associate professor or everything else being equal. Same year of experience, same years of service, they teach the same discipline, they have the same rank. The male will make $4,783 more than women. And so this is the kind of interpretation you get here. And so what this one says is an assistant professor makes 12,000 less than an associate professor because our basis here is associate professor. The one you are missing is your basis. So everything is built on top of the one, the basis, the one that you are missing. Okay, I hope this is clear. So I want you to understand these coefficients and their interpretation, especially the categorical variables, what do they mean? They are just binary, they become 0 or 1 in the model. Now, the standard error, you already know it, so the t-value, let's forget about that. And then we look at the p-value. So this model is telling us that this is significant, this is significant, this is significant, and so on and so on. Except the gender, the sex isn't significant. So now I needed to modify my model because I include sex here. They are telling me that the gender isn't significant, that this 4,700 you see, it is just due to, it is by chance, okay? So if you get a different data set, you will not find that difference. So men don't make more than women. This is what the model is telling us, that this difference that we find, it is just coming from chance. So basically what it means is I should remove it. Oh, I wish I could edit it easily. So what it is telling, I should remove it. How do you change the color? I should cross it here. It don't have it in the model. So the model should stop here, because it is not significant. And the only significant element are this. And this model gives us an adjusted R square. This model gives us an adjusted R square of 0.44. So the salary of someone can only, 44% of the variability in the salary can only be predicted using these parameters. So we still have 66% or 65.37% that is not explained by the model. It is explained by other things. Other things that we don't know, we don't have them here. And like always, you can still check some residuals and their behavior. And yeah, let me just float that one. We call it the so let me. Any question meanwhile?
All right, so far no one. Someone is.
Okay. I'm listening.
Ajoke, did you want to ask a question?
No, I'm saying no question.
Okay.
So let's plot our residuals and see what we can see if our model makes sense.
No question.
Okay, sounds good. So let's say
someone has a question.
Okay, go ahead.
An issue with line 42, says Adeyumi.
If you have an issue on line 42, then the issue should be on 41. What is the error you get?
Error in summary salaries. Object salaries LM not found.
Yeah, because you did not create it. So the way in 41 is different from the way you called it on 42. It will need to be exactly the same name. So check the spelling.
Okay. It's the same thing.
So make sure you run line 41. Run it again.
Okay. I was able to run 41.
Okay, run 42 again now.
Error.
Okay, so hold on. I will finish with what I am doing, and then I come back to this specific case. Okay.
Okay. Thank you.
You're welcome. So now maybe we want to see residuals, and one way to do it is maybe the most complicated way, in my opinion, but that's what I think as well, that she has different naming. Because when the object is not found, it means that the name are not, the spelling isn't exactly the same. So, and R is case sensitive. I don't know if you already know it. So case sensitive means if you use a capital in one case and you use a small caps in the other case, it is not the same object. Not all languages are case sensitive, but so one way we can do it is let's just plot this, all salaries LM, and see what we get. If we get something good, it is good. If we don't, it is not good. So it says a return. So we can do return, and we get them being plotted one by one, residual versus fitted, and so on. And return again. So this is our QQ plot. Return again, and this is a scale location. I will explain them later one by one. And this is a residual versus leverage, and that's it. So we have them differently like that. What about we do what we did before? How many were they? And
4.
Yeah,
4.
that's not what I did before, but I want to do this just for
2 by 2.
testing. So the good thing coding in front of other people learning is they learn how the process, like the thinking behind it. So like you see, I plotted first, and I know that there are 4, and I want to check them. And now I am saying empire 4, and then what is the code that I used before to do something like that? I will just plot, and then I say which, and just give them. So which, and I say 1 to 4, and let's see if it works. It worked. And we have an extra cook distance. So maybe it is not 1 to 4. There is one that is missing. Anyway, we are getting something that we like. And residuals versus fitted. Now notice one thing that is a bit different from what we had before. Here we have like chunks. It is because of some categorical variables. So with the categorical variable, it will be the same thing, and then you get different responses. Like if it is male, it is still male for all of them, but you get different responses, and you have something like this. So this model, like this cloud of point data above here shouldn't be there. So that's a problem in the fitted, and the model is telling us to check the point 365, the point 250, and the 44. And when you look at the QQ norms, this one should be normal. And all this deviation doesn't help to really feel good. But it is not a big suggestion because the majority of points are on the line here, so we can tolerate it. But this is something that we needed to double check. In reality, you will never find the data that is really normal like this line. So it is something we can accept. And then scale and the location. This is a huge problem. It feels like as values are getting higher, the residuals are getting higher, and that shouldn't be the case. It should be a flat line, and we don't have it. So this is an issue that we need to think. Maybe there's something we need to do with the high values, and there is still maybe one predictor that could help that we did not include. And I think that's the most important element you need to consider when you are talking about multiple regression. And that's it. And these things that are done directly by R, you could change them. And there's another thing that maybe you will find somewhere in the literature. Before going, I will have to show it to you. So there's something known as interaction. Because the way it is done now, what about the interaction of someone? Let me try it first, and then maybe I can talk about it. Instead of changing the model, I will just copy it. I think I only have 1 minute left, so I will hurry up. So I only do interaction between a rank and the discipline, and everything else I leave it like that. So what we should see here is more elements, no? Yeah, so now you have the interaction element that I added. What if someone is, like what is the interaction between being the discipline and the ranking? If you are older and teach a discipline. So this is difficult to interpret, but it is something that you can see else there. So if you do, I think it is too many predictors. Let me select just two of them that were highly significant, the rank and the discipline. And so the rank and the discipline, and I remove everything else, okay? So we still see that the intercept is significant, the rank is significant, and the discipline is significant. But the interaction, I don't know how to explain the interaction in this case. So the interaction is like, does the rank goes up as the discipline goes from A to B? That's the idea of interaction. And they are saying that no, there's no strong relationship like that, that one doesn't drive the other. For example, if we don't have like people going from one discipline to another, then the interaction, the ranking as professor changes. Maybe discipline is a bit difficult to understand. So let us say that I was using years of experience and years of service. This is something that is going to be maybe different. No, years of service, no, years since PhD, and then the rank. Even the other one, the interaction isn't significant either. But this one is easier to explain. So the idea is, does it go like the rank? Do you become like associate professor since you, if you have more years since you got your PhD? This one intuitively makes sense because to become associate professor, you need to spend a lot of time after your PhD. But the model is saying that that doesn't really affect your salary. It is not like you become more associate professor because of the number of years since you got your PhD. So that interaction doesn't really affect your salary. And I just wanted you to know that data exists out there, and you will see many models doing the interaction. And it is the same with ANOVA, because the only thing I needed to change it to have these models as ANOVA is, I think I need to add ANOVA. And I know we didn't talk ANOVA, but I told you it is exactly the same model. And now you have it as ANOVA. How do you call ANOVA now? I forgot. But a summary, right?
Yes, we use summary.
Oh, I don't know why.
Yeah,
it's not.
AOV also does.
But I think with the AOV, you don't need the LM. If you put LM, you will get an error.
Yes.
Oh.
You will get it.
Okay, that sounds better. So with analysis of variance, now we have that years since experience, the rank is significant, and the years since experience doesn't matter that much. And then you have the interaction doesn't matter that much either. So these two models are telling basically the same story, but this one is more emphasizing on the rank. And I think this one, linear regression, is really giving you the effect of each element, rank as associate professor, rank as a professor, and then the intercept that is in this case, associate professor. Yeah. And that's all for me. And I am happy if you have more questions to explain about linear regression and the advanced models that you can use that are still linear though, that you can use in using massive data set. Because one assumption that this linear or multiple linear regression suppose is your number of observations is larger than your number of predictors. So let's say that in this case called salaries, our data set, we have 397 observations and only 7 variables. Let's say that we had only 7 observations and 387 observations, then we couldn't use a linear regression. It is not just feasible. Because you have too many predictors that depend on few observations. So you will have infinite many solutions. So that's not going to work. In that case, you need to go to more advanced linear regression models that I am not covering. We did not cover here. So all this supposes that you have more observations than predictors. And I think I will stop here because more I talk, I think more you will get confused. And
can I already add? I mean, not really add, but I'm not sure if I missed just it, but did you mention that? Whoa.
Oh, sorry, I forgot there is a video.
Did you mention that like when you are talking about the variables that were transformed into 0 and 1, did you mention that that is actually the dummy variables you mentioned before? Or
Yeah,
is it actually?
I talk about the dummy variable, but you are right. I think I could have gone a bit deeper in the details of how it is done. But since I know that I will do it for them, I didn't want to confuse many people.
Yeah,
So,
I just wanted to mention that this is what is called, if you will do it yourself, dummy variables, right?
Yeah, I said it when I was presenting in the PowerPoint and like the slides.
Yeah. Okay.
Hello.
Yeah. Another name, okay, before I give you the microphone back, another name you find in the literature is what is called one-hot encoding. So it means like transforming this categorical variable into 0 and 1.
Okay.
But that's another name you will find in the literature. Yeah, that's all for me. And the floor is yours for questions. I know there was one student who had a question.
Please let's try and ask our questions. But sorry, before we give room for questions, Mr. Martin.
Yeah.
I would like you to maybe do like a brief run through residual analysis. Why do we have to carry out residual analysis? I know we didn't really cover some of the tests that we could actually do, like Chapero week and some other ones that we can do to test.
I think even in real life, you don't do those tests either. They are just academic teaching to check the normality. But in reality, you don't do the test and then carry another test to check actual normality of the residuals. You check them because those tests themselves have some assumptions on the data. And in the statistical world, those tests are not meant to be conducted on residuals. They are meant to be conducted on actual data set. So like Shapiro tests and things like that. They are meant for actual data. So the right and the best way to check the assumptions on your model is to check the residuals. And you check your residuals visually, not by carrying actual tests to report the p-values and like you will do Shapiro test and then you are like, okay, the p-value shows that my residuals are normal. That's not the right way to proceed. If you do something like that, it makes you feel good, but statistically it is flawed because that test wasn't developed with that intent. So the intention of it is the right thing to do is to do like residuals versus fitted, to do the normal QQ plot, and then check the ordering of residuals and what is the fourth. I think that's it. And it is graphical and visually. And so it is left to the interpretation of the analyzer. I know that you would like to have a strong and a definitive test that says, yes, it is normal, no, it is not. But in reality, you don't do that because that is just a flawed test.
Okay. One other thing I also want you to make clear to the participants again is, for instance, the model we have just built predicting salary with all these other independent variables. Let's take, for instance, that we have to build like 4 models. And the task is now to judge the model that best predict, that best fit to the data set. So in that case, would it be better for participants Will it be better for us to stop at the level of R square? Or we talked about
So
archaic information
I
okay.
I believe
think,
this will be covered next time, right? On nonlinear regression.
I think the question is relevant here as well, and I alluded
Okay.
to it during my presentation where I talked about model selection. So the question is, if you have a lot of predictors, how should you proceed into, because you cannot integrate all of them, like we said. And by the way, talking of that, what is the R square of the model where this is a PhD? The R square was a bit lower. So adjusted R square. And that's why I said adjusted R square is a good predictor. And it is not the only one. We could use a AIC or BIC. But in this case, the adjusted R square, because it is taking into account all those nonsense and unuseful parameters. Sorry. Now that you brought it over, since we found that, let me go back.
Okay.
What kind of error is this? So since we found that gender isn't that significant, the best thing to do normally is just to remove it and rerun our summary without it. Because this is only adding some kind of noise in our data set, and it is increasing the variance. And we don't want to increase the variance. And we get this new model that has an adjusted R square of 0.44. And the R square of, we don't care about that one anyway. So let me compare it with what we had before. So it didn't change anything because it wasn't affecting the decision. But yes, if you have a lot of predictors, the best thing to do is to run a linear regression one by one. So you will run the first linear regression. Are you going to cover better set selection, forward, backward, better set?
Didn't plan that, but
this is advanced material as well. So it is quite tricky to not cover, to talk about these things and try to stop short, not going to exactly, because there is a really good, many good methods for set selections, and they are known as best set selection, backward set selection, and forward set selection. And so that's what I was saying. The one way you could do it is you run it one by one, and then you get which one is a stronger predictor. So like the rank by itself is giving us an adjusted R square of 0.39. So you can then put yes since PhD. And I mean, with R, this one you can automate it. You can have a for loop that does it automatically and then select what is the highest. You don't have to do it one by one. And this one gives us 0.17. So we know already that the previous one that was rank is more important than the PhD. So we can know which ones to prioritize. So using rank is more important than yes since PhD in our model. Okay. That's one way we could go detecting only a few of the predictors. Another way is what we call a setup selection. That is like you start with a model. Who has the background noise? You start with a model that is empty, like you know that if I do just this, I will get an empty model, right?
This is all instead, yeah?
Yeah. Huh?
I think with dot it's all.
Yeah, I think null or zero, I don't remember. Yes. So here you just get the intercept. That's it here. So what the forward set selection does is like this. It just started with a model where it doesn't put any predictor. That is like the bias, just the intercept, and then get the R square associated to it. And then we'll put one of it one of them will put rank, and then we'll remove rank, put each one of them, and then add the second one, add the third one, and so on, and build the model until to see which one will give them the best R-square or the best BIC or IC, because that one you have to specify yourself which criteria you want to use. And I feel like it is a bit beyond the scope of this training, because I don't think it is more difficult than this, but I feel you have to have the foundation and then you need to understand it step by step. But if we have another training that is going to build on top of this level of training, I will be happy to talk about those things.
Okay.
More questions, sir?
Yeah, questions? Any questions?
Adewumi, did you manage to fix your problem?
Yes, I fixed it. Thank you.
You're welcome.
Okay, Mr. Martin. I don't know, maybe this, what I'm just trying to do is I'm trying to ensure that participants, as much as some of them are new to coding and programming with using R, I also want them to at least, if not understand the practical aspect for now, they can get to understand the theory behind it.
Yeah.
So
I agree.
Yes, I just want to talk about RMSC, the root mean square of error. In some papers, they use that. They said they use that in judging maybe this model is better if we have a low mean square, root mean square error. If we have like 4 models and we have this one with the smallest root mean square error, most times some of those people will report it that no, that one with the lowest is the best.
Okay.
What can you say about using RMSC, root mean square error?
I think there is a confusion here, because there is a confusion right now, because that kind of analysis and that kind of report goes a little bit beyond fitting a model. Because this one, to explain it, I needed to go back. So we have 700. We have let me go back to my data set. We have 397 observations. So we will need to split this data set into what is known as training data set and then test data set. In fact, normally you have to have it in 3 categories: training data set, validation data set, and the testing data set. But let's suppose you don't have enough data. So you will only have training and then test data set. And then you build your model using the training. And you build your model using the training, and then you have to use the remaining of the data set to check how good your model predict the values. So that one goes a little bit beyond fitting linear regression. But it is a way to check the validity of your model out of sample. It is known as out of sample validation. Because if you only check it on the same data set, then you are not doing anything. So root mean square error is how well your model is predicting the data that it never saw. So for example, this model, so if we feed it new like a salary and A and B and so on, how well will it, no, not salary. If we feed it the rank, the discipline, years since experience, how well it will predict the salary. And then we can use it to judge how the model is performing. So that's fine. But that's what I tell you. As long as you do it, it is not, let me scale down and say that that is only valid if you are performing it on a test data set that the model never saw, first of all. Second, that test data set needed to be representative to the actual data set. So some people, I can cheat it. It is easy to cheat it. You just need to select the data set that is on average the same data that is the model saw. So that your predictions will be very close to the training itself values. But in reality, that's not easy to get in real life. So I am not saying it is not the right way, but it is what is known in data science as validating a model. And then, because you are opening a door, that is the next step. What if you don't have enough data, right? Then you can use what is known as cross-validation. So cross-validation is basically trying to remove the data, predict it. So, so I don't know how many people are interested. I see the number is going lower and lower. So the cross-validation idea is you have your data set. Let's say we have 387 or 97 observation. If we need to split it, then we need to take like 20%. That is 40 at least. 40 times 6, that's 100. And we only have 200 to build our model. So less data you have to build your model, less stable and less good your model is. So you have that challenge between taking some data to validate your model or using all the data to build a very robust model. So the middle ground between it is having what is known as cross-validation. It's like instead of taking all the data out, or I will explain the concept of leave one out of cross-validation. So you will build your model using 396 observations and then predict one that you left out and then compare it with the actual and calculate the error. And you do it for the 397 observations. So you will get an error. That is one way of validating your model as well. And you do it for different models, and then you can select the model that gives you the smallest root mean square error or mean absolute error. So those are, that's why I said that it is not a linear regression. Then we go to what is known as model selection. And those methods are not only suitable for linear models. You could use it for non-linear models that Doji will present. You could use it for more complicated models like neural network, random forest, and so on and so on. Or even classification. That is not, right now we are talking of regression or prediction. And you could do prediction. You could use it for classification where the outcome variable is 0, 1, or I don't know, male and female. And so those techniques are not reserved for linear regression. So that's why I didn't go there.
Okay.
Actually, I don't know how much do you expect from the next session, but for now, I have one example of model selection, but I mean, I was not planning to go into any details of which different ways you have to select model and so on. I was going to talk about AIC and RMSC. I mean, since I also used AIC like in my last two studies, I could say something more about it and so on. But as Bagaram just said, there are different ways you can use to select a model, the best model and so on. And I think having these basic ideas that he just explained is useful.
I mean, the danger I can find is trying to present a lot of things to people and
exactly.
They don't understand anything.
Yeah. So, that is why it's better to just keep it simple and make it possible for them. Okay, now that they heard about it, they can go and learn more about it.
Okay. I think that is very clear to all the participants. Yes. Yeah, you know, one of the things I'm glad about is people are really getting a lot from this training, and that is the beauty of it. People are giving feedback as to how the training has helped them introduce them to R. And one very, very, very salient information and drive that one I've gotten from this is maybe there might still be need for us to maybe organize a basic class of which we'll do that like a basic. where we'll talk about the basics before we'll now come and build on what we have done in this AREFOR20. So we might go back a little to do some things on basic things on coding with R, and subsequent training after that we can move into something advanced. So do we have any other question again before we close? Our time is fast spent, and I don't really want to stress the trainer too much so that he can have some time to sleep and also enjoy the watermelon, even though he doesn't call us. He does the trainer doesn't invite the participants to come and join him because he knows if he invites us, we will finish it. That will not be enough for him. So, but we are happy.
You got it right.
So please, I want somebody from the participants to just talk. Like, let's have your feedback as to this training before we close. Just one person. It could be a feedback. It could be a word of appreciation. It could be something. Let's just have you say something. Anybody? Okay, let me use. Okay, good.
Well, so I really want to appreciate the organizers of this training. I also have a trainer. So today, so little time, squeezing so much, you know, I see a lot of optimization and all this. So thank you. I hope you understand.
Yeah, and Bagaram also because he was there.
Yeah. So thank you so much, and I do believe that with a little more effort on our part, we will be able to catch up and also build ourselves to get to the level that you have. So thank you very much.
Thank you so very much. So once again, I want to appreciate our trainer for today, Mr. Martin Bagaram. I've been blessed, and I'm sure every other participants too have been really, really blessed. So I can easily say I need to go back to some papers and so this is what this means, this is what that means, and feel free. Let me also say this: Mr. Martin is on Instagram. What's this? LinkedIn. And if you have any challenge, any question you want to ask as regard the training, you can add him up on LinkedIn with Martin Bagaram, I think. Is that the name on LinkedIn?
Yeah, Martin Bagaram. Yeah. You can shoot me an email on LinkedIn and or a direct message on LinkedIn, or I just send you an email, and I am responsive with emails. I'm not responsive with the chats. So even if you find my Facebook, don't try to write me, because it is very likely that I will not even answer on your Facebook or your WhatsApp, because to me those are for fun stuff, and so you shouldn't write me because you feel bored. You should write me because you want to talk to me. So that's the difference. If you write me an email, then I know that you thought about it and you mean what you are saying. And if you just shoot me a message on Facebook, it will go to, I will not respond. Very likely I will not respond.
Okay. Thank you very much. So we can copy Mr. Martin's mail address from the chat.
That one I want to.
Yes, so we can copy Mr. Martin's mail address from the chat room, and whatever questions we have, we can direct it to him, and I'm sure he will reply us. So once again, I want to appreciate us. Let me also thank Mr. Kofi. We did this whole thing together. We moderated today's training together, and we started with a co-founder, but due to some logistical issues, she had another thing she quickly had to attend to. So on her behalf, I want to say thank you to every one of us. And let me say this: God bless you. God bless you.
It was a pleasure for me to share this with all of you.
Oh, thank you, sir.
Thank you, and take care. And I really appreciate our friends from Nepal. They are already gone. That could join us. That's nice. And thank you.
Okay. All right.
God bless all of you. Bye.
Thank you. Bye.
Okay. Bye-bye.
Bye.